So in the previous video we've seen how, starting from a Lie algebra, one can determine a set of roots. So the way we did this is we found some maximal set of commuting generators in the Lie algebra. So in the case of SO5, which is a rank 2 Lie algebra, one could find 2 Cartan generators. And then one can look at the simultaneous eigenvectors of these Cartan generators in the adjoint representation. And we know that the remaining generators of SO5 have to decompose into these eigenvectors, and they'll have eigenvalues which are called the roots, alpha, which are vectors in in this case a two-dimensional real space, because the rank is 2. And these roots, they're nice vectors that group into these nice symmetrical figures. Here's another example. This is an exceptional Lie algebra, which is denoted by G2. It also has rank 2, and if you determine the roots in this particular Lie algebra, so this Lie algebra now has dimension 2 plus 12, so dimension 14, because it has 12 roots and 2 Cartan generators. So dimension 14 and rank 2. Now its roots have this nice hexagonal structure. So what these two examples seem to indicate is that the roots of a Lie algebra have to satisfy very stringent properties. The way that they, the angles that they form between these vectors. And this turns out to be true. In fact, the roots of a Lie algebra always form a set of vectors that is known as a root system. So let me give you the definition of this. Definition: a root system phi of rank R, it is a finite subset of the R-dimensional real space, except for the origin, satisfying following properties, which are really quite stringent. So first of all, phi spans the real space. So if I take all these vectors, then by taking linear combinations I should be able to get any r-dimensional vector, which is certainly the case for these collections of vectors. The second is that the only real multiple of a root in phi that is also in this root system is minus alpha. So here we can see this is true. The only vectors that live in the same one-dimensional subspace are just the reflections of these vectors. The third condition is that for any two roots alpha and beta, if we compute the inner product of alpha with beta divided by the inner product of alpha with itself, then this is going to be a half integer. So what does this really mean? Well, note that this combination, it is really about projecting the vector beta along the vector alpha. So in particular, if I draw this here, this particular vector, this projection, that is exactly alpha dot beta over alpha dot alpha times alpha. So this real number, it really measures the length of this projected vector compared to the length of the vector alpha. And it's saying that it always has to be a half integer multiple of alpha. And if we look in these examples, at least if I've drawn them accurately, then this is really true. So projecting this vector, say on this horizontal one, it should be exactly a half as long. While if, for instance, I project this vertical vector onto this diagonal one, it is exactly the same length. So here, values that we obtain for this ratio are either 1/2 or 1, or if I project them onto an opposite one, they can also be -1/2 or -1. And projecting, say, two orthogonal vectors, then the inner product is going to be 0. And similarly here. And then finally, for any 2 roots phi, we will also have that beta minus this particular combination of alpha is a root. So this combination, this is called the Weyl reflection of beta in the plane orthogonal to alpha. So it's the reflection of beta in the hyperplane that is orthogonal to alpha. So let's look at this particular picture. So this hyperplane orthogonal to alpha, this is the blue plane. So how can I get the reflection of beta in this plane? Well, exactly what I have to do is first I project it onto the plane, which is really taking beta and subtracting this projection onto alpha. So then I get a vector in the plane. But to get the reflection, I have to subtract it again, right? So then I get this vector. So it's really subtracting the projection onto alpha twice, and then I get the reflection of beta. So this is the Weyl reflection. Okay, so my claim is root systems of rank R are in 1-to-1 correspondence with compact Lie algebras. So this is something or one part of the statement I announced in the previous video, namely that if I know the roots of an algebra, then I can actually reconstruct the full Lie algebra structure. And in the exercises you're going to check this at least partially for SU3. So the other part of this statement is that for any Lie algebra, if I take its roots, that it really satisfies all these four properties. So this is the part that I want to prove here. So I'm not going to prove that any set of roots satisfying these properties is actually realized by a Lie algebra. Okay? So there are a couple of steps to this. So let's look at the okay, so let's prove that the roots of a compact Lie algebra form a root system. So let's first look at the first point. So we have to show that these roots of the Lie algebra span the r-dimensional linear space. So let's use a contradiction argument. Suppose that our roots do not span this space. So if they do not span this space, it means they span a lower dimensional subspace. And whenever you have a lower dimensional subspace in some vector space, it means you can always find a vector that is perpendicular to the whole subspace. And suppose it does not span. So this means that there exists some beta, an r-dimensional vector beta, that satisfies that beta dot alpha is 0 for all alpha, for all roots alpha. Okay. So what does that mean for, let's say, a particular generator? So let's look at the generator beta I contracted with the Cartan generators. And let's see how they act in the adjoint representation. So we know, of course, that since the Cartan generators commute with each other, this vanishes identically. So we only have to check what the action of this linear combination is on the vectors that correspond to the roots. So beta I, hi acting on E alpha. By construction, the roots are the eigenvectors, the simultaneous eigenvectors of the Cartan generators. So this is just beta I alpha E alpha, but by our assumption that vanishes for this vector beta. So what does this mean? This means that I have a Lie algebra element that annihilates all vectors in the adjoint representation. So this is saying that this element beta I hi commutator with any element in the Lie algebra is 0. So really this is called a nilpotent element. And if you recall from last time, the nilpotent elements in your Cartan killing metric correspond to zeros on the diagonal. Right? This is really equivalent to saying that if I take the Cartan killing inner product with any vector x, it is equal to 0. because this Cartan killing inner product was really defined in terms of the adjoint representation of this on other vectors, but that's identically 0. But this is in contradiction with the compactness. Because remember, compactness was stating that this inner product is negative definite. Negative definite. So it does not have any nilpotent elements. Okay? Now the other three properties, they will be a consequence of identifying various copies of SU2 within any Lie algebra. So the other properties will be consequences, will be of the presence of SU2 subalgebras in G. So let's see exactly what this means and where are these SU2 subalgebras. In particular, so if we find SU2 subalgebras, we can use what we know about the representations of SU2 to say something about the root vectors. So where are these SU2 subalgebras? Well, in the last video we've already seen that these root vectors, they group up into raising and lowering operators, which do not raise by 1 or lower by 1, like in SU2, but they raise in the direction, say, of a particular root that you've singled out. Okay, so let's make this precise. So for a fixed root alpha, let's write E plus minus to be the same as this generator E plus alpha or minus alpha, but let's normalize it properly. So we normalize it by the norm of this vector alpha. So this is just a Euclidean norm, the length of the vector. And let's write E3 to be alpha I for the norm squared of alpha hi. So what I claim is that these satisfy exactly the commutation relations of the SU2 algebra. Okay, so that means E plus E minus is E3, and E3 E plus minus is plus minus E plus minus. So this is exactly what it means to be a representation of SU2. Like we said, a set of matrices, linear operators, is a representation of SU2 if it satisfies the commutation relations of SU2, so the particular structure constants of SU2. And in terms of these J3 and J plus minus, these commutation relations read exactly like this. So let's see that this is indeed the case. So the first thing we notice is that if we look at the commutator of E plus and E minus, then this is by definition hi E plus alpha over, let's write alpha squared, and then here E minus alpha because of normalization. And in the last video we already realized that if you take this combination, then it will be an eigenvector with eigenvalue that is plus alpha plus minus alpha, so it's 0. So it's a eigenvector that has eigenvalue 0 of hi, so this is 0. So this implies that we have found a vector with 0 weight, and by definition a vector with 0 weight, it's in the Cartan subalgebra. So E plus E minus must be in the Cartan subalgebra. So to determine exactly which Cartan generator this is, what we really have to do is take the inner product of this state with the Cartan generators and then see what comes out. So let's compute hi with this commutator E plus E minus. So by definition of this inner product, this is the trace of hi multiplied by the commutator E alpha E minus alpha. So let's rewrite this trace a bit by expanding the commutator. So we have 1 over alpha squared trace hi alpha E minus alpha minus the opposite order. Okay. And now we can use the cyclicity of the trace. So I want to write this as 1 over alpha squared trace, where I put the E minus alpha on the left hand side. So let me just cyclically permute these matrices that I'm allowed to do within the trace. Then I get here hi E alpha, and for the second term I get E alpha hi. So this is really the commutator of hi with E alpha. But we know what this commutator is. This is alpha squared, so trace E minus alpha E alpha by construction of my states E alpha. And recall also that E minus alpha, we had chosen the basis such that this is the Hermitian conjugate of E alpha. So this is really 1 over alpha squared of the inner product of E alpha with itself. But we had also chosen these to be normalized, so this is equal to 1. Right, so this implies that E plus E minus is oh wait So this is of course not E alpha, it is alpha I times E alpha. We have alpha I. So to get this particular vector, we know that the coefficients in front of hi are going to be alpha I over alpha squared. So this is alpha I over alpha squared hi, as we claimed. So this is E3. So how about the second part? Well, this part is easy because we know what the commutator of the Cartan generator with E alpha is. For the second part, we say that E3, let's compute this, E plus minus. So that is alpha I over the norm to the third, bringing those parts out. H of I, E of plus minus alpha. And this is plus minus alpha I over the norm to the third times E plus minus alpha. And let's see. So this should be equal to plus minus E plus minus. Is that correct? Yes, because here I have the norm squared divided by the norm to the third. So indeed, this is plus minus E plus minus. So by choosing one particular root alpha, say this one, then normalizing the corresponding generator and taking also the root minus alpha and some linear combination of the Cartan generators, we get an SU2 algebra. And what does this SU2 algebra do? Well, these E plus minus operators, they really move the other roots by a value that is equal to alpha. So let's see what the consequence for this is. So consequence. So we have now these three SU2 generators, which, I mean, these are still operators that act on the Lie algebra because this is the adjoint representation. So that means that all the vectors in my Lie algebra, they have to group into irreducible components of SU2, so into spin J representations. So the generators Hi and E alpha have to group into irreducible representations of SU2. So into spin J representations. And this is going to imply directly for us these properties 3 and 4. So let's see why. So 3 and 4 follow directly from E of beta living in some spin J representation. Right, and let's see. So I claim that any for any root beta, this E of beta is going to be an eigenvector of E3 just by plugging in the definition. So E3 was alpha I over alpha squared hi acting on E beta. By definition, E of beta is an eigenvector of the Cartan generators. So this is alpha dot beta over alpha dot alpha acting on E of beta. So we found a vector in our vector space that is an eigenvalue of the E3 generator of SU2. It's an eigenvector of the E3 generator. But we know exactly what the E3 eigenvalues are, right? In every spin J representation, they're going to run from, so this is M, they're going to run from minus J to J with integer steps. And J had to be half integer. So the only possible eigenvalues of E3 in any representation of SU2 is half integer. M has to be half integer. And that is exactly point number 3. Now, how about point number 4? Well, I mean, this is, again, easy when you realize this. So, E of beta, it will live perhaps in some linear combination of spin J representations. But anyway, it's going to live at the eigenvalue M. So, okay, remember in SU2 we have M running from minus J up to J. So perhaps this vector E of beta is living here. But then we know that we can just lower this this vector E of beta by applying E minus to get to a state at minus M. So by performing the lowering operation exactly 2m times. So we also know that if we apply E minus 2m times to E of beta, then that is the, right, it cannot vanish, and it will be proportional to a root vector, where now this is lowered by 2m times alpha, and it cannot vanish. Right, but this is the m was alpha dot beta over alpha dot alpha. So we're going to find a root vector with root which is exactly this Weil reflection. So this reflection in the plane perpendicular to alpha. So this has to be part of G by construction of the SU2 representation. Now finally, let me not prove part 2. And also I did not prove for you that for any value of the root there is just a single root factor e of alpha. But this again follows from the SU2 representations. So essentially the idea is that if you have some vector alpha, and suppose there would be another vector that is a linear multiple of this, then because of the possible eigenvalues that E3 can take, it can only be an integer or half integer multiple. So suppose I would have another vector with, say, that is twice as long as alpha. Then I could use E minus on this vector to lower it towards alpha and then lower it further until it has weight 0, so it's in the origin. But one can actually show that such a vector will vanish by just computing, just like we did before here, the inner product of the generator with the result of applying E minus to this vector. But that is not possible, because if I have a vector that lives somewhere in my spin J representation, then, and I apply my E minus to it until you hit m equal to 0, it cannot vanish there. Because if applying E minus to a vector would make it vanish, then it would be a lowest weight. But the lowest weight is minus j. So for any vector with eigenvalue m, you can lower it at least to minus m, as we did here. So it cannot vanish at 0. So this is not a possibility. Okay, so that finishes essentially the proof that the roots of a Lie algebra really satisfy these stringent conditions. And then in the next video, we'll actually draw some conclusions from these conditions.